So in this video, we're going to find the local maximum and minimum values and saddle points of our function. Then we're not going to really graph this, so we can ignore all of that, and then we have to enter our answer. If we don't have a saddle point or a local maximum or local minimum, we just say we don't have one, so D&E. So our function f of xy is xy minus 2x minus 2y minus x squared minus y squared. We want to find our partial derivatives, so let's do that. Partial derivative with respect to x is treating y as a constant, so this is going to be y, and then minus 2 minus 2x. Let's see, let me make sure that's correct. So treating y as a constant, so x is 1, so it's just y, minus 2. Okay, that's correct. And then y is treating x as a constant, so it's just going to be x, and then minus 2 minus 2y. Very similar to the previous one, just replacing the x's with y's. Now we set these equal to each other, or rather equal to 0. And, well, effectively we set them equal to each other. If we set both of them equal to 0, we can do that. But what we will do instead is we will try to solve this as a system. So the way we solve this as a system is we just basically we can bring this 2 on the other side. So it's going to be y minus 2x is equal to 2. And then this one, so that's what that becomes, and this one becomes x minus 2y is 2. So we can solve this as a system now, so we can set it up. So y minus 2x is equal to 2, and negative 2y plus x is equal to 2. We can multiply this by 2 if we want to. So that's 2y minus 4x is 4, minus 2y plus x is 2. And then we can go ahead and add these. So negative 4x plus x is negative 3x, 6. Let me make sure my arithmetic is correct. So 2 minus 2 and then negative 4. Negative 3. Yep, that looks correct. So this is going to be x is negative 2. That's just our x value. We can take this value of x and substitute it and plug it back into one of these equations. So I'll plug it back into this equation. So that's going to give you y minus 2 times negative 2 is 2, which is y plus 4 is 2, which gives you y is negative 2. So that's your y value, that's your x value. So we have our critical point. So this is our critical CP, critical point of negative 2, negative 2. That's the critical point that we get. So we have to determine if it's a local max, min, saddle point, or if we can't determine it at all. So let's see. We want to find d of xy, which is f xx times at xy times f y at xy minus fxy squared. First of all, finding fxx, it's not too hard because we already have fx. So fxx is, again, this partial derivative with respect to x. So it's treating y as a constant, so this is constant minus 2. So this one, treating x as a constant minus 2. And then fxy, treating y as a for this expression, treating x as a constant. So it's constant 1. So this gets you to d of xy is equal to fxx is just negative 2 times negative 2 minus 1 squared. That gets you to the value 4 minus 1, which is 3. Now the values that we need to see is d of -2, -2, and fxx -2, -2. This we know whatever value of x and y, it's always going to be the constant 3. That's what we saw here, so it's 3. This we don't know. We have to figure it out. Well, it's also a constant. As you can see here, it's also -2. It's just a constant, regardless of what we plug in. And since this is greater than 0, and this is less than 0, that immediately tells us that this is going to be a relative max. So we know now that we have a relative max at the critical point of -2, -2. But we don't know the value of the relative max just yet. It's not too hard to find. Just plug it in. So it's going to be f of -2, -2. So -2 times -2 minus 2 times -2 minus 2 times negative. Let me make sure that's correct. -2, -2, minus 2, -2, minus 2, -2, minus -2 squared minus -2 squared. It's a lot of -2's. So this is 4 plus 4 plus 4 minus 4 minus 4. 4 plus 4 plus 4 is 4 times 3, which is 12. Minus 4, 8. Minus 4, 4. Or we could just do like cancels this, cancel this, cancel this. That's just 4. Same thing. So we have relative. This is our relative maximum value. And we get this value at our critical point. But what do we want? We want to find the local maximum minimum values. And so this is our relative maximum or local maximum value. And we are done with this problem.